So before we talk about specific scheduling algorithms, I want to talk about scheduling criteria. And these are important. The goals of scheduling depend significantly on the objectives of the system. First, you have to decide what you want. If the system is supposed to respond to events within a certain period of time, it makes it a real-time system, and that's something you'd like to know when you're choosing what scheduling algorithm you want to implement. Maybe the goal is to maximize CPU utilization, like in a supercomputer, or maybe the most important thing is for users to feel like the system answers them quickly when they issue a command. Right? We have to decide what we want, and again, as usual, when making a decision, we can choose randomly, but that's kind of silly, so obviously we won't do that. But what we actually want is evaluation criteria, right? Given a scheduling algorithm and recognizing that there is no algorithm that is perfect for every scenario, what would we be interested in? What are the things that we could maximize, minimize, balance, avoid, all those things? And there are 9 criteria that we are going to talk about in this discussion that are potentially interesting in terms of evaluating a given scheduling algorithm. And I'll try to give a brief rundown of each of these things. Number 1 is turnaround time. And turnaround time is the amount of time between starting a thread and when it finishes. So this is the execution time plus the amount of time waiting for resources, where resources are things like processor, I/O, etc. So wall clock time matters here. And that's important to users, right? All things being equal, a user wants their task to complete as fast as possible. If I ask my computer to convert a file from, say, FLAC format to MP3 so I can put it on my phone, what I care about is the turnaround time. How long will it take to convert this file, right? You watch the bar move from left to right, it gets to the finish, and we're done. Item 2 is response time. And assuming that a process is not a background process, this is the time between putting in a request and getting some answers back. And a process can often start producing output while still carrying out the request. So if I'm searching for a file on disk, while the search continues to run, any results that have been found so far can be shown in the results list, and we'll just keep filling in the rest of the results as they arrive. Response times are very important to users. If they click a button and it takes a long time for that to get acknowledged, users get frustrated and they sometimes issue the command more than once. It did happen to me a number of years back that I accidentally bought 2 train tickets via an Android app. This was a single ride ticket, so it was only a €5 mistake and not a monthly ticket, which could easily have been a €100 mistake. So yeah, response time actually matters. Number 3, deadlines. This is much more of a concern for real-time systems that have hard wall clock deadlines. If I'm watching a movie and I have to, if I'm watching it on a physical Blu-ray disc, the player needs to read the data from the disk, decrypt it and decode it, and display it to the screen within a certain period of time. Otherwise, the quality of the video is degraded. Maybe the Blu-ray physical disc feels a little bit silly to talk about right now, but certainly if I am trying to watch some encrypted content because it's from a streaming service and they don't want me downloading it and putting it on a pirate website, right? Like my computer has to decrypt the received content and show it to me on the screen in a way that meets the deadline. Otherwise, it looks funny. I get the little loading bar or something. Number 4, predictability. It is desirable if a job runs in a fairly consistent amount of time. If a task normally takes X minutes and right now it's taking 2X minutes, then somewhere between that X and 2X, the user might think the process is stuck and might terminate it because users are impatient. Number 5 in the list is throughput. Scheduling policy should try to maximize the number of threads that complete in a given amount of time. It's a way of figuring out how much work is actually being accomplished, right? It's a way of assessing how much we're getting done. Much depends obviously on the nature of the threads, but all other things being equal, we would like to accomplish more in the same amount of time. If I'm in line to renew my driver's license at Service Ontario, if Service Ontario office increases their throughput, more people get their requests finished during the day. If it has a low throughput, I might be waiting there for an absurd amount of time, which would never happen. Definitely not. Number 6 is processor utilization. This is obviously the amount of time that the CPU is busy. As we already mentioned, supercomputers are expensive to build and maintain, and processing time is sold or leased to various organizations like a research lab or a university. And any time that the supercomputer is not doing useful work is wasted, because that's money that we could be earning. You get the money. So we give a lot of priority to keeping it busy. Number 7, fairness. Who could be against fairness? The problem is we don't necessarily all agree on a definition of fairness, right? What seems fair to one person maybe doesn't seem fair to another, and this is sometimes why we have to go to court. What we do expect, though, is that threads should get at least a basic level of fairness, right? And basic level of fairness means threads don't starve. There is a story, it might or might not be true, about a system being shut down in 1972 that had an as-yet unexecuted job that had been submitted about 5 years earlier. I think we can safely call that unfair. Number 8, enforcing priorities. Processes and threads can be assigned priorities, and priority will get some more discussion later, but it's just a way of saying this process or thread is more or less important as compared to others. Scheduling should respect this within reasonable limits. One example of priority within reasonable limits is something like priority boarding if you fly on a plane. Those who get priority boarding get to go on the plane first. This has some advantages. If overhead bin space, a resource, is limited, well, getting on first helps in getting that. But everyone who has a seat on the plane will eventually get to board and arrive at the destination, assuming they're not having a freak out at the airports and getting themselves on TV for being a giant Karen. Nevertheless, the highest priorities process or thread should probably run most often or first, but it shouldn't always be the one selected. Just being the highest priority doesn't necessarily mean it's going to run 100% of the time, because this might violate the principle of fairness. And then there is balancing resources. And we'll get a better outcome if we balance the resource usage, where the better outcome is improved performance. The example we mentioned above applied. We would like to choose some CPU-bound and I/O-bound threads, so both the CPU and I/O are kept busy. If we have more information about the I/O that the threads need, so much the better. If we can choose a thread that's going to use the printer, and we know the printer is idle, that's great. If we know that a thread wants to use the network, but the network is busy, maybe we don't choose that one. So those 9 things are basically criteria that we can use to evaluate a given scheduling algorithm and see how well it meets our goals. Now, scheduling algorithm goals really depend on sort of what system it is, and I think it's fair to say that all systems care to some degree, not zero, but not necessarily in equal amounts and not necessarily in this order, about fairness, priority, and balancing resources, right? We have to deliver at least a minimum level of fairness, or we would like to anyway. We need to respect priorities. Priorities are not everything because that conflicts a little bit with fairness, but at least it has to be taken into consideration. And then making good use of the resources makes a lot of sense. For batch systems, and batch systems are the kind of thing where you submit work and then it's processed and then the result is sent to you later kind of thing. We care a lot about throughput, we care a lot about turnaround time, we care a lot about CPU utilization, right? We're trying to maximize the usage of the resource, where the resource is the computer, and so accomplish the most amount of work that we can accomplish in this time, and also get it back to you as quickly as possible. And then there are the interactive systems, and for interactive systems, we are interested in talking about, well, response time and predictability. Right? As a user, when I'm working on an interactive system, so it's talking to me on the command line, or I'm clicking things in the UI, I care about the response time. I want to know that my input has been accepted, even if the response isn't ready yet. And I also want it to be predictable, right? When things are going unexpectedly slowly for some reason, like I feel frustrated, and as a scheduling algorithm, I want to avoid the user frustration. Before we go on, I want to talk about priorities, the use and abuse thereof. So we've said that processes and threads have priorities, and I've referenced now more than once that priority is important, but we didn't actually give it a lot of definition. A process has a priority, and that is typically an integer. Whether a higher number is a higher priority or a lower number is a higher priority is a question of system design, and just as in England they drive on the left and in Canada we drive on the right, when there's two ways to do something, there will inevitably be two implementations. So in Unix, a lower number indicates a higher priority. In Windows, a higher number indicates a higher priority. Why? Because that's why. Now, with a priority value assigned, it can be used to make certain decisions, right? If process P1 wants a resource R1 and P2 wants that same resource, where the priority P1 is greater than that of P2, we can choose to assign the resource to P1, and that respects the priority, if you will. This might come into play as an example when two threads are waiting on a semaphore. If process P3 posts on the semaphore, the resource of that signal may be sent to the higher priority process P1, allowing it to proceed first. And again, out of the way peasants, a high priority thread is coming through. Now, the operating system or the program author may each be partly responsible for assigning a priority to a thread. And these priorities can change over time and when certain conditions are fulfilled. For a process that uses a lot of CPU, it might be temporarily reassigned a lower priority by the operating system to not let that process monopolize the resource. Similarly, system administrators can change priorities of threads or process, and users may also have a say in this regard, but in a limited way. In Windows, for example, as a user, you can set a task to a higher or lower priority, but giving this to users was probably a bad idea because they often do it wrong. If you have a long CPU-bound task, the right thing to do is actually to give it a low priority and not a high one. You might expect the high priority makes things go faster, but it hurts the performance of the system and it makes users kind of unhappy. And so the existence of priorities does mean that some processes are treated better than others, and sometimes this is solely the result of inheritance. And if you find yourself in this situation in real life, it's like, why is that person considered important just because their family is a royal family? You might have questions about that. But this does actually happen. We haven't talked about inheritance for priorities yet, but we will. So, as I said, users have a say in priority, and they can get it wrong, so we shouldn't let them. We can expect that a high priority task will execute more, and maybe it slows down the performance of the system, and users are sad, even though that's explicitly what they asked for. Now, in some systems, and I'm sure I mentioned this much earlier on when we talked about switching between processes, like all the way back in the processes topic, where we said, okay, the highest priority non-blocked process will always be the one that's chosen to run. That is a great way of making sure that processes that have the highest priority have the right of way. They get to go first, they get to do what they want, but it's a terrible way of ensuring fairness and preventing starvation. So scheduling is not as easy as just always finding the highest priority thing to do. And in our next topic, we're going to start looking at some actual potential scheduling algorithms, things that will be used to make decisions about what we're going to do to try to balance all of the criteria that we have talked about before this.